Hello everyone. In the previous session we have discussed the application of electrical analogy method to a combination of wall or slabs which are in a series as well as parallel combination. Now we are going to apply this electrical analogy to hollow cylinder. So for this purpose, we need to take some things, some physical aspects into consideration. For a hollow cylinder, there will be some internal surface, there will be some internal radius, and then there will be some thickness of this hollow cylinder. Above it, there might be some insulation provided on this piping to avoid heat loss. It can be a very practical example of a steam pipe in industry. So, this will be first radius R1 of the hollow cylinder. This will be second radius, which is outer radius of the cylinder or that pipe. And this will be the third radius because of presence of insulation. Let us consider that steam is flowing through this pipe at a temperature T infinity 1. Also, because of fluid movement, there will be some heat transfer coefficient H1. Let us say the length of the pipe, which is perpendicular to the plane of the paper, is L. So L is the length of the pipe that we always consider. Okay. Now, because this fluid might be heated or it might be cold, so internal surface temperature of cylinder will also have some value. Let us say it is equal to T1. The external surface of cylinder, it is at temperature T2. The outer surface of insulation, it is at temperature T3. Also, there will be some external fluid, T infinity 2 and H2 will be the properties of that external fluid. Now, if I write this external fluid on this side as well as T infinity 2 and H2, still it doesn't matter because both sides of this pipe, they are exposed to the same fluid. So steam might be flowing through this pipe and atmospheric air might be in contact with the outer surface of cylinder. So now what we will do, we will create the thermal resistance network and see how to evaluate this. So as we know, the heat transfer, if we want total heat transfer, it is simply the delta T divided by summation of all thermal resistances which come into picture. Whatever are the thermal resistances in that particular path. So let us begin with our thermal resistance network. Let us start from T infinity 1. So this will be our first junction, T infinity 1. Please don't worry about the thickness of that resistance. We are more interested in the concept. Resistances actually help us to convert this complicated system into simpler system. So what we get here, this will be first thermal resistance up to point T1. From T infinity 1 up to T1. Now from T1 to T2. From T1 to T2, there will be this second point. From T2 to T3, there will be the third resistance. Now, there will also be the thermal resistance between T3 and T infinity 2. So, there will be one more thermal resistance. This will be T infinity 2. Okay. Now, even though all of them are thermal resistances only, but still their physics is different. For example, the first thermal resistance is because of convection. Second thermal resistance is because of conduction. Third thermal resistance again conduction, and fourth one again convection. Let us consider that for the cylinder thickness, K1 is the thermal conductivity of cylinder material, K2 is thermal conductivity of the insulation material. So this will be first, because it is convection resistance, so we will write it Rc1. This is conduction resistance, so we will write it only R1. This is again conduction resistance for the insulation, we will write it as R2, and this is second convection resistance, so that's why we will write Rc2. So that's why what we observe, all the resistances are in series. Because of this architecture, heat will flow through the cylinder, which can be evaluated with the help of this formula. Whatever be the heat flow, it is equal to the potential difference or temperature difference divided by summation of thermal resistances. So what can we write? And as we have understood already, हमें जितना भी पैसेज कंसिडर करना है उतने पैसेज का हमने टेम्परेचर डिफरेंस कंसिडर करना है. So we are going to consider right from the beginning until the end. So all the resistances will come in picture. If you are considering between T infinity 1 and T2 only, then you need to consider only these two resistances only, not R2 and RC2. So I can write over here, it is equal to T infinity 1 minus T infinity 2 divided by whatever comes into picture, whatever comes in the path. So first one, there will be convection resistance on inside, then conduction resistance of cylinder thickness, then conduction resistance given by insulation, and convection resistance on the outside. This will be the magnitude of heat flow rate through the cylinder. Now we will see how to quantify each and every one of these quantities. First one is RC1. For your information, I will write it once again. It is convective resistance. So because of that, its fundamental formula for any geometry is 1 upon HA only. But in this case, we are talking about internal heat transfer coefficient and internal surface area. We know for a cylinder area is a function of radius. As the radius changes, area changes. That's why this is a very important physical consideration. Unlike the plane wall, in case of plane wall, area was constant, but in this case, area will not be constant. So that's why if we are writing convection resistance first, which means for inside, it means we have to write this entire 1 upon HA for inside, or 1, it will be 1 upon H1, which is heat transfer coefficient at the inside, and the inside area A1, it will be equal to 2 pi R1L. Remember, for all the thicknesses, for all the radii, length will remain constant. So this will be the total convective resistance for the inside of this cylinder. So the first quantity we have evaluated. This is done. Now we will go on to R1. Notice that R1 is conduction resistance. Firstly, we will understand the physics and then we will convert it into appropriate mathematics. So now, but even if it is conduction resistance, now we will analyze the geometry. This is not a plane wall. So we will not use L by KE. We know that by Fourier's law of conduction, heat transfer from cylinder is 2 pi Lk delta T divided by ln of R2 by R1. So in this case, when we rearrange the entities, keeping delta T in the numerator, everything else in the denominator, what we get is thermal resistance by conduction for a cylinder, it is equal to ln of R2 by R1 divided by 2 pi Lk. This will be conduction resistance for a cylinder. Same physics we will apply over here. So what do we get over here? Conduction resistance for the first thickness of the cylinder. Means we are now considering only this portion of the cylinder, the portion which is indicated by the hatching lines. Only this much portion. So for this, now notice one thing, this ln of R2 by R1, it means that, it doesn't mean that every time R2 by R1 will be there. R2 is actually the outer radius for that particular cylindrical section, R1 is the internal radius. K is the conductivity of that particular material only. L is constant because it is same for every section, 2 and pi both are constant. So in this case, for this particular section that we have indicated by hatching line, R2 is the external radius, R1 is the internal radius. So the formula for this R1 will be ln of R2 by R1 divided by 2 pi L K. But K for this first section is K1. In the same fashion, we can write down the conduction resistance for the second thickness. This is nothing but thickness of insulation. So I am talking about this particular thickness. So The basic formula will remain same, only internal parameters will change. R2 is again a conduction resistance for, let us say, second thickness or for insulation. So in this case it will be ln of, now for this section actually R3 is the external radius, R2 is the internal radius. So that's why the formula will become R3 divided by R2 and 2 pi L K, this K of this insulation now, not this K. So it will be K2. This will be R2. So now we have our third formula with us. So in this way we have quantified the conduction as well as convection resistance for the cylinder. One quantity which is remaining is outside convection resistance. Again, physics is convection resistance. So fundamental formula will remain same, but it will be applied to the second section, which is outer surface. So we can write RC2 is equal to 1 upon HA, but this will be not only HA, this will be H2A2, and as we know, this outer surface area of the cylinder will be 2 pi R2L. Sorry, my mistake. The outer radius of the cylinder, total outer radius is R3. So instead of R2, it will be R3. Even if we have written this as A2, still the basic concept does not change. We can write 2 pi R3L, or you can write it as A3, that is up to you. So that gives you RC2. The second convection resistance is 1 upon HA, outer surface area we are talking about. So that will be H2 in 1 upon H2 into 2 pi R3L. So we can log this formula. Now we have RC1. Yes, we have R1S, we have R2, then we have RC2. On the basis, we have evaluated the entire denominator. So if we are provided with the value of T infinity 1 and T infinity 2, we can immediately calculate the heat transfer from this hollow cylinder. And if any other quantity is missing, then we can also evaluate that. The most important understanding in this case is only this physics, that area is a function of radius, area changes with radius, it is not a constant area, and that is what we have to take care. Whenever we write the basic formula at any section, we have to substitute the properties of that particular section. Firstly, we understand the physics, then we write the formula for that particular section, for that particular geometry, then we substitute the individual parameter values considering the diagram, and that's why it is very necessary to draw a schematic diagram so that you don't miss on a single point. If a problem statement is given and you do not draw such a diagram, then it will be almost next to impossible to write down all these formulae, because there are many numbers and quantities. So if you draw a diagram, it becomes very simple. So see, such a complicated geometry, such a complicated physics, but converted into a very sweet, very small mathematics, and it can be solved easily. I hope this is useful for you. Thank you.